Today on the AI Paper podcast, we are breaking down MOVA towards scalable and synchronized video-audio generation by the SII OpenMOSS team. If you build generative media, you're going to want to hear this. Here's the 60-second download.
MOVA is basically the first big open source model. We're talking 32 billion parameters that generates high-quality video and perfectly synchronized audio at the same time.
And at the same time is really the key here. This is not another cascade. It's built on what they call an asymmetric dual tower architecture. So you've got a big 14 billion parameter video DIT and a smaller 1.3 billion parameter audio DIT. And they're connected by this bidirectional bridge module.
And to make that work, they came up with two really clever tricks. First is aligned rope to handle different frame rates. And the second is dual sigma shift, which, well, it stops the video training from just completely overpowering the audio training.
The result, state-of-the-art lip sync, state-of-the-art temporal alignment. It's beating models like LTX2 and, frankly, any cascaded pipeline you could build. The weights are out, the code is out. So let's get into how they actually pulled this off. All right, welcome to our deep dive. So to really appreciate what MOVA is doing, I think we first have to talk about the mess we're in right now. If you're using open source tools to make a video with sound, you're basically on an assembly line.
It's a very disjointed workflow, yeah. You're almost certainly using what's called a cascaded pipeline.
Which means I generate my video first, right? Maybe with something like OpenSora, I get that looking good, I freeze it, and then I pass it off to a totally separate audio model.
Exactly. You take your silent movie, you hand it to, say, Audio, and you just sort of hope for the best. You say, please, guess what this should sound like.
And the problem there feels really obvious when you say it out loud. The audio is just reacting. It's totally downstream.
It is. There's no bidirectional interaction. The audio model can't turn around and tell the video model, hey, I'm about to generate a really loud sound. You need to open the mouth wider. The video is already set in stone.
Which leads to what they call drift.
Drift? Yeah. The lips are moving, the sound is happening, but the phonemes, the sound shapes, don't quite match the V-seams, which are the visual shapes of the mouth.
It looks like a badly dubbed foreign film. So MOVA just throws that whole assembly line out. They're trying to build a single brain that thinks in pictures and sounds simultaneously.
That's the goal. And they do it with this asymmetric dual tower design.
Okay, so let's visualize this. We have two towers side by side.
Right. On the left, you've got the heavyweight, the video tower. It's about 14 billion parameters, initialized from 1.2.1, and its job is to handle all that really heavy geometric denoising.
And on the right?
On the right is the audio tower. It's much, much smaller, only about 1.3 billion parameters.
So why the big size difference? Why not make them equal partners in crime?
Well, because the jobs aren't equally complex. I mean, think about it. Generating photorealistic video at 24 frames a second is it's a much heavier computational lift than generating clean audio.
Okay, that makes sense.
If you made the audio tower 14 billion parameters, you'd just be burning GPU cycles for, very little gain. It's about efficiency.
So it's efficient, I get that. But if they're separate towers, how do you stop them from just becoming another cascade? How do they actually talk to each other?
That is the secret sauce. That's the third piece of the puzzle. Sitting right between them is a 2.6 billion parameter bridge module.
So a translator.
A very, very active translator. It uses cross-attention. So at every single step of the diffusion process, the video tower is sending its hidden states over to the bridge, which then informs the audio tower. And at the exact same time, the audio tower is sending its states back across the bridge to the video tower.
Wow. So while the video model is literally deciding how to draw a pixel on a lip, it's also hearing the audio model getting ready to synthesize the right sound for that lip shape.
It's hearing it, and the audio model is seeing the mouth open. It's a completely unified process.
That sounds incredibly elegant, but I imagine getting two different types of networks to, synchronize their watches is a complete nightmare. I mean, video and audio don't even live on the same timeline.
Not even close. It's like they're in different universes of time. Video is coarse, right? You've got discrete frames. Audio is dense. It's a continuous waveform. Or, latent tokens that represent tiny slices of a second.
So if you use a standard positional embedding, like ROPE, the kind we see in all the big language models, it just completely falls apart here.
Completely breaks. In an LLM, it's easy. Token 1, then token 2, then token 3. But here, let's say token 10, in the video tower might correspond to the half-second mark of the clip,
Yeah.
but token 10 in the audio tower might correspond to like 1/100th of a second.
Oh, I see. So if the bridge just naively connects token 10 to token 10, it's connecting the middle of the video to the very beginning of the audio.
Precisely. You get this massive temporal misalignment. The model just has no idea when anything is happening relative to anything else. And the MOVA team solution for this is called aligned row B.
How does that work? Is it complicated?
The math has some details, but the concept is actually pretty simple. It's all about stretching one of the rulers. They just calculate a scaling factor, let's call it Sealer, which is just the audio frame rate divided by the video frame rate.
So they're just scaling the video's position numbers to match the audio's grid.
That's it. They map the video's positional indices so they land on the exact same temporal coordinate system as the audio. So if video token happens at the same physical time as audio token J, aligned row B make sure their positional embeddings reflect that.
That feels like something that should be standard, but it's really interesting they had to explicitly engineer that in. Okay, so that's the alignment problem. The other huge innovation here is how they solve what you could call the training speed problem.
The dual sigma shift. And honestly, for anyone out there trying to train their own multimodal diffusion model, this might be the most important part of the whole paper.
This is that calculus versus painting analogy you mentioned, right?
It's a perfect analogy. Training a model to denoise video is hard. Training one to denoise audio is also hard, but they're very different kinds of hard.
Right. Video needs really heavy denoising. You're building complex 3D-like geometry out of pure static. You need a very strong signal to emerge from the noise.
Whereas audio, especially for things like timbre, the texture of a voice is incredibly sensitive. If you hit the audio latent with the same amount of noise you use for video, you destroy all the fine-grained detail. You get a voice that sounds like it's been run through a cheap distortion pedal.
So if you chain them together with a single time step, a single T, and force them to learn at the same pace, one of them is going to suffer.
One of them will always suffer. If you tune your noise schedule for the video, the audio sounds terrible. If you tune it for the audio, the video comes out looking blurry and undefined. So Anovia decouples them. They don't sample one time step $2. They sample tier veils for video and tele for audio independently.
And that's what lets them apply these different sigma shifts.
Exactly. The sigma shift just controls the noise distribution. For the video tower, they slam it with a shift to 5.0. That is super aggressive. It forces the model to focus on the noisy end of the spectrum, which is where it learns structure and geometry.
And for the audio?
They started off gently, a shift of just 1.0, a much smoother, more forgiving schedule.
But they don't leave it there, which I found interesting. The paper talks about this 3-phase training curriculum. And in phase 1, there was a detail about the text prompt that really stood out to me.
You're talking about the text dropout.
Yeah. A 50% text dropout rate. That means half the time, the model doesn't even see the user's prompt. Why on earth would you cripple your model like that?
You do it to force dependency. It's like, think about learning to lip read. If I give you a perfect transcript of everything I'm saying, you're not going to bother looking at my lips, are you? You're just going to read the transcript.
That's a great point. So by hiding the text prompt, they force the video tower to look at the audio from the audio tower to figure out what's going on.
Precisely. If the text prompt, "a man is laughing," is hidden, but the audio tower has a strong laughter embedding, well, the video tower has to use the bridge to get that audio information so it knows to generate a smiling face. It makes the bridge a structural necessity, not just an option.
That is seriously clever. It stops the two towers from just learning to ignore each other. Okay, so what happens in phase 2?
Phase 2 is all about quality refinement. And here's the twist. They actually crank the audio sigma shift all the way up to 5.0 to match the video.
Wait, but you just said a shift to 5.0 fries the audio.
It fries the audio if the model hasn't learned the fundamentals yet. But once that basic alignment is locked in from phase 1, ramping up the difficulty forces the audio tower to get really, really good at denoising complex signals. And that's what fixes the timbre and makes the voice sound rich and natural.
And phase 3 is just scaling up?
Just pure scale. They bump the resolution to 720p, use longer sequences, and bring in context parallelism. But all the real intelligence, all the sync logic that's baked in during those first 2 phases.
Let's switch gears to the fuel for all this. The data. We always say data is king, but for multimodal AI, it really feels like the biggest bottleneck.
It is the bottleneck. You can't just scrape a bunch of YouTube videos and call it a day.
Because a huge percentage of video on the internet is, from a data perspective, just complete garbage.
Total garbage. Think about a music video. You see a person walking down the street, but the audio is a clean, studio-recorded drum machine. If you train on that, your model learns that the sound of walking is a kick drum.
Or bad dubs, or background noise, or...
Yeah. So the MOVA team started with over 100,000 hours of video. But the real magic is the pipeline they built to filter it. This gauntlet is almost as valuable as the model itself.
A 3-stage filter, right?
Yep. Stage 1 is just basic data hygiene, resizing video, voice activity detection to find speech. But Stage 2 is the killer app. They use a tool called Synchformer.
And that acts like a bouncer at a club.
That's a great way to put it. It watches the video and listens to the audio. If they're not perfectly, and I mean perfectly, synced, if there's even 100 millisecond lag, which is super common online, it throws the clip out.
Wow. Ruthless.
You have to be. Garbage in, garbage out. If you train on out-of-sync data, you're just training your model to generate out-of-sync video. But my favorite part, honestly, is how they handled the captioning. They set up these specific laws for their captioning models.
The law of visual truth and the law of visual silence.
Exactly. So they have separate models captioning the video and the audio. But they gave the video captioner a very strict rule. Do not hallucinate sound.
What does that mean in practice?
It means if you see a dog in the video, but the dog is not barking, you cannot write a dog barking. You can only write a dog. And conversely, the audio captioner was told, if you hear a bark but you can't see a dog, do not write a dog is visible.
Okay, why is that distinction so important?
Because you want the model to learn the correlation, not the assumption. You want the bridge to learn that it's only when the audio features show a bark and the video features show an open mouth that those two things belong together. If the text caption creates that link for it, the model gets lazy.
So it stops the model from just hallucinating a dog every time it hears a bark, even if the bark is coming from off-screen.
It keeps the modalities honest with each other. And then finally, they use GPT-OSS to merge those two sets of clean, separate captions into one coherent narrative prompt.
So you have the architecture, the training strategy, the pristine data. Now it's time for the moment of truth, inference, actually generating a video.
And this is where they pull out another really cool trick. It's called dual classifier free guidance, dual CFG.
Right. We all know CFG. That's the knob in Stable Diffusion that lets you trade off creativity for strict adherence to your prompt.
Exactly. But normally, CFG is a tug of war between two things, your text prompt and, well, nothing, an unconditional generation. MOVA has 3 players in this game. They have text conditioning, which they call text dollar. They have the null conditioning, and they have the bridge conditioning.
So you can separately control how much the model listens to my text prompt versus how much it listens to the other modality coming across the bridge.
That's it, exactly. And when they started playing with this, they uncovered this massive fundamental trade-off that anyone using this model has to understand. You basically have a sync knob and a quality knob, and they are constantly fighting each other.
How does that work?
Well, if you crank the bridge guidance way up, set it to a high value like 4.0, the synchronization metrics go through the roof. The lip sync becomes, mathematically, almost perfect.
That sounds like what we want. That sounds great.
It sounds great on paper. But when you actually listen to the output, the audio quality tanks, the voice sounds robotic, processed.
Wait, why would making the sync more perfect make the audio sound worse?
Because the model starts over-optimizing for geometry. It's forcing the audio waveform to bend and twist to align perfectly with every single video frame, and it sacrifices the natural, organic, slightly messy fluctuations of real human speech to do it. It's prioritizing being perfectly on time over sounding good.
Wow. That's a really profound insight. It's like the uncanny valley of timing. Real people aren't perfectly synced machines.
Not at all. So they found a sweet spot. Usually, keeping the bridge guidance a bit lower than the text guidance gives the best results. You want enough of that connection to keep the lips moving correctly, but you also need to give the audio enough freedom to breathe and sound natural.
Okay, so let's talk bottom line, the results. How did MOVA actually do against the competition?
They put it in the ring against LTX2 and a standard cascaded pipeline. The main metric you want to look at is LSEC, or lip sync error confidence. Higher is better.
And the verdict?
MOVA hits around 7.89 with that high guidance setting. The baselines were, well, they were significantly lower. Yeah. But numbers are one thing. The real test is always the arena, the human evaluations.
And did people actually prefer it?
Overwhelmingly. In head-to-head comparisons, users consistently chose OVA for, and this is their term, speech-to-mouth tightness. It just looks more real.
There was one last detail I saw about the user experience that I thought was pretty funny. They basically admit that users are terrible at writing prompts.
Oh, yeah. We just type a man talking.
Right. So they actually built a prompt rewriter into the pipeline.
They did. If you feed MOVA a really simple prompt, it uses an internal LLM combination of Qwen3VL and Gemini to look at the first frame and expand your prompt into a rich cinematic description. It helps the model better align with all that super detailed training data we were just talking about.
It's a bridge between a lazy user and a very sophisticated model.
That's a good way to put it.
So let's bring it all home. MOVA is open source, 32 billion parameters, and the weights are available now.
Which is just a massive contribution. I mean, until now, if you wanted this kind of high-fidelity sync, you were probably looking at a closed API like Veo or Sora. This puts that power into the hands of the research community.
What's the biggest takeaway for you from this paper, beyond just the specs?
I think MOVA proves that multimodal can't just mean let's glue two models together. The bridge architecture really shows that for temporal tasks, for things that unfold over time, you need a shared, deeply integrated processing. You need a brain that is fundamentally wired for both sight and sound from the ground up.
It really challenges that modular Lego brick approach we've seen dominate open source for a while.
It does. But it also, and I think this is so important, it highlights that tension we just talked about. The tension between perfect synchronization and acoustic fidelity.
The robot versus the soul.
Exactly. As we get better and better at forcing these models into perfect mathematical alignment, we have to be really careful we don't optimize all the life out of them. A perfectly synced video that sounds synthetic is not a win.
It's a fascinating question for the field, isn't it? Are we training these models to be perfect, or are we training them to be human?
And I think the answer to that question is going to define the next generation of these models.
Well, for all the researchers listening, the weights are up, the architecture is public. Go see if you can break that bridge.
Or build an even better one.
That's our breakdown of MOVA. Thanks for listening to the AI Paper Podcast, and we'll catch you on the next one.